Did you know a significant bottleneck in deep learning performance often isn't the model architecture itself, but how we prepare and augment our training data? Most manually designed augmentation strategies are far from optimal. This challenge led to a powerful yet under-discussed technique: automated data augmentation policies, specifically methods like auto-augment and its efficient successor randaugment. Instead of just randomly flipping images or adjusting brightness, these approaches learn the most effective sequence and intensity of data transformations. At its core, auto-augment frames data augmentation as a search problem, where a controller neural network explores a vast space of possible augmentation operations and their parameters, like rotating an image by 30 degrees then increasing its contrast by 50%. This controller is trained using reinforcement learning, optimizing for the best validation accuracy on a proxy task. It generates an augmentation policy, a list of subpolicies, each defining a pair of operations and their probabilities. For example, imagine training a model to detect rare diseases from medical scans. Data is scarce and privacy-sensitive. Instead of a standard fixed augmentation pipeline, auto-augment could discover that a specific sequence of subtle geometric distortions and slight color shifts, combined with a particular probability, significantly improves the model's ability to generalize to unseen patient data. This learned policy creates diverse yet realistic variations of existing scans, effectively expanding the dataset and boosting diagnostic accuracy. Traditional methods rely on human intuition and extensive trial and error, often resulting in suboptimal and brittle augmentation pipelines. Automated policies, by contrast, are data-driven, discovering nuanced transformations that human experts might overlook, yielding superior performance and robustness, particularly critical in fields like autonomous driving or medical AI. However, auto-augment's initial computational cost was immense, sometimes requiring thousands of GPU hours. This led to innovations like randaugment, which simplifies the search space by uniformly sampling from a set of operations, greatly reducing computational burden while often achieving comparable or even better results. This makes automated augmentation practical for a wider range of projects. Ultimately, these techniques compel us to rethink data preprocessing, not as a static setup step, but as a dynamic, intelligent component, an active participant in model optimization. They show that even the input to our AI can be intelligently crafted by AI itself, pushing the boundaries of what's possible with limited data.